next project up, we have Mr. Tim and Takeo with ball bots. Are you guys ready? All right.
Okay, hi everyone. This is our SBI project we've been working on for the past couple months. It's called Ballbot. I'm Takeo, this is Tim, and then we have a third member, Arnav, who can't be here today. So our project began in January when we all participated in a hackathon, and we really enjoyed the experience, so we were looking for a project we could try next, and we came across this MIT Maker Portfolio robot. It's like a one-wheeled system. Bunch of motors, really complicated. It didn't work in the video, but that kind of got our minds turning, and we found this genre of robots called ballbots, and we thought we'd make our own version of that.
So you must be wondering what ballbots actually are and what they actually do. Well, many people have attempted this in the past. In its essential form, a ballbot is a single-wheeled balancing robot that tilts and rotates in order to counteract this innately unstable system. So the primary goals of these robots are to, firstly, achieve a stable balance, and secondly, be able to control its movements through tilting in certain degrees and directions, as well as rotating itself. The advantages that these robots have over typical robots are that it's omnidirectional, meaning that it can turn very easily on the spot, whereas a typical four-wheeled robot might have a turning radius. It's also very tall, so it can interact with people better. And its high center of mass is actually not a problem, but rather it plays in our favor because you can kind of imagine the analogy of it being easier to balance a meter stick on your finger than a pencil. These ballbots typically have four major sections in their systems. Firstly, they always have a power supply or a battery. They always also have a processor or a microcontroller on board. And then thirdly, they have some kind of system of sensors. In most cases, it's an IMU in combination with a lot of encoders for each motor. And then finally, they have some kind of actuating system, which is a combination of motors, omni wheels, and the actual ball that we're moving in order to reorient our robot. So does it actually work? Well, here's a quick clip that Takeo and I took pretty recently, just this past week, of one of our better trials. So you can see here, this is the robot, and I have it in person now. It's on top of a soccer ball, and it's spinning its motors in order to rebalance itself every time it starts to feel like it's falling over. So this was a pretty long run. It's one of our better runs we've had. It's around 10 seconds balance. You can see it moves around a good amount. So yeah, hopefully we'll try and show you guys that in person later, but probably not here, maybe outside later. Yeah.
Okay, so we're gonna want to go over the different subsystems of our robot. So we'll go over the mechanical, electrical, and control system aspects, and then we'll take you through some of the results we've achieved thus far, and then the challenges we faced, and what we see as our next steps. Starting off with the mechanical design, there were two main drivers that affected this. The first was to keep it modular so that we could efficiently iterate on our design, and the second was to place as much mass as high up as possible for the reasons Tim mentioned earlier. The chassis is fully 3D printed, and then the tower plates are all laser cut acrylic. And then, yeah, so using that CAD screenshot, that CAD file you've seen, we were able to use that alongside with taking real-life mass measurements of different parts of our system. And from that, we were able to gather all the system parameters we needed to fully inform our system dynamics. So that includes masses, measurements of like radii, and like different lengths between center of masses. And with that, we were able to also calculate moments of inertia using our CAD file.
Now for our electrical system, as Takeo mentioned, it was very simple and a modularized design. So we mostly used a lot of breakout boards, but for all our circuitry, we used pretty temporary setup with breadboards and perf boards. We have three different DC power rails, 3, 5, and 12 for our multiple logic levels and our motor drivers. And then finally, we chose the TT3.6 as our MCU, mainly because it had an onboard native SD driver that would allow us to read data during our live runs. So in our quick system block diagram here, this is a pretty generalized version, but you can pretty much just see that it's a battery powering up our MCU, our sensors, and our motors, and then our sensors are reading back data into our MCU, which we're feeding back in order to create driving PWMs for our motors. So definitely the hardest part of this project was learning controls because we're not very experts. We didn't really know a lot about controls going into this project. So going into the control system, our real physical bot is obviously in 3 dimensions. I'll take it out later so you can see. But because it's in 3 dimensions, it gives us a pretty complex control system. So instead, in order to simplify things, we decided to split things up into 3 individual planar models. This kind of just means splitting up this three-dimensional object into 3 different planes, and then we're going to control each plane independently. So what this is going to give us is 2 inverted pendulums in the XZ and YZ planes, which in the ideal world are identical, and then 1 yaw control in the XY plane, which is kind of a bird's eye view if you look at it from the top to the bottom. So right now we have 1 3-dimensional control system split up into 3 individual 2D control systems that we're going to try and control. So those are 2 inverted pendulums and then one yaw control. So from those planar models, we derived a lot of physics equations. However, we want to model this in controls, so we decided to go with a state space model in order to model our physical system with matrices. These use state space variables, which represent system dynamics. So example of the equations that we have in our case is shown at the top right here. And then from our actual state space model, we need to implement a controller, so we chose to go with an LQR controller, which is a type of full state feedback, which basically just means that we're constantly updating and reading all of our states with each loop. It's also a form of optimal control, which means that it's going to minimize a cost function J, shown on this slide here, that will help maximize performance, aka reducing error, while also minimizing our actuator's effort or our motor's efforts. The result in our case is something similar to PD control, however, this isn't always the case. This is a pretty rough drawing of what our control system looks like. This is, just keep in mind, this is only for one of our inverted pendulum planes, so we actually have 2 of these. The primary key concept here is the LQR balance controller, which I mentioned. That outputs a torque, which we convert into our plant or our state space model. After actuating our system, we feed back the readings from our sensors in order to get a good state estimation for our angles from vertical and also our robot speeds. And then that creates an error that we will feed back into our balance controller. So currently, we're only focusing on balance. We're kind of ignoring position and yaw control. So basically, it can move around as much as it wants or spin around its z-axis as much as it wants, because we want to focus on the balance first, and then we'll introduce those later. All right, so here's a couple of results. Firstly, here's a simulated system initial response in MATLAB. This is to an initial state of a 10-degree tilt, which basically just means that we're simulating our robot having a 10-degree initial tilt, and then we're seeing how our control loop with our unstable system responds to that. So the red box plots are kind of what we want to focus on more. So firstly, theta is the angle from vertical in one plane, of course, in our or I think this is the YZ plane. So theta, you can see, starts from a non-zero angle, which is 10 degrees, and then it comes down to 0 pretty quickly, so we're pretty satisfied with that. You can see something similar to theta dot, and then finally torque is what we're writing to our motors, so it's showing how much we need to actuate our motors in order to be able to return our system to balance. We've also included the LQR matrices here. These you can kind of just think of as weights or weighting matrices for our cost function, which tells you how much we value balancing our robot versus how much we value minimizing the effort involved in running our motors.
Here we're showing you guys a plot of some real test data we've taken when we've actually ran our robot. In orange, you can see the angular displacement in the YZ plane, and then in blue you can see the torque response from our controller. And intuitively, it kind of makes sense. You see that when there's a large angular displacement, you see our control system reacting and trying to reach stability again. Yeah, moving on to the main challenges we faced during the project. The first and major one would be our motor characteristics. We observed really poor torque performance at low PWM duty cycles, and we also ran into another problem kind of alongside using PWM duty cycles, PWM signals to control our motors that inherently control voltage, whereas our whole control system is outputting a torque, which requires current control from our motor controllers, which currently we're not able to do. And then self-inflicted challenge was we mixed up degrees and radians a lot, which was really tough for debugging purposes. And finally, a couple times we noticed our motors were demanding more current than our motor drivers could supply, which basically meant we had to replace our motor drivers 2 or 3 times. And yeah, those are the main challenges we faced. Yeah, and moving on to next steps, the biggest thing we see helping our robot's performance is to implement that current control motor driver that I just mentioned. We think that will have really large effects in our performance. And alongside that, we want to also start implementing the XY yaw control, which is kind of the first step into possibly branching out into position control of our robot, which means it can actually control its position and move around to different locations. down the line, we might also want to start developing a 3D model, 3D state space representation of our robotic system, which is definitely the most encompassing and accounts for all the coupling effects between the split up planar model we're using now.
Okay, yeah, so that kind of wraps up our presentation, but we're not going to do a live demo here because I don't think we can on this ground, and it's kind of hard to see, so we might do it outside later. Well, I'm just going to take it out of this package to show you guys what it actually looks like in person, but feel free to look at it more later. Here's this guy. It's pretty weighty, which kind of helps in our favor, because I think the more mass it has, the more time it's going to take to fall over, and our motors are pretty strong, so they're pretty beefy. They're able to drive our